So let's take a look at the formation of imines and enamines. These are formed by reacting aldehydes or ketones with amines under mild acidic conditions. We'll start with an example of imine formation. These are produced by using primary amines, reacting it with an aldehyde and an acid catalyst. You can see the product looks pretty similar to our starting material, but the double bond is between the carbon and nitrogen, whereas our aldehyde starting material, the double bond is between the carbon and oxygen. Now, for enamines, the conditions are pretty similar to imine formation, except we need to use secondary amines. Notice that we still have a double bond in our product, but the double bond is instead between two carbons, our original carbonyl carbon and its adjacent carbon. So the important thing here for these reactions are you'll need an aldehyde or a ketone with an acid catalyst along with a primary amine to produce an imine, or a secondary amine to produce an enamine. And also keep in mind the difference in the location of the double bond in imines and enamines. In imines, the double bond is between a carbon and a nitrogen. And with enamines, the double bond is between the original carbonyl carbon and its adjacent carbon. Next, we'll take a look at the mechanism to produce an imine. Let's get into the general mechanism for imines. As we go through, we'll label each step and we'll draw the lone pairs on all the heteroatoms to satisfy the indicated formal charges. But before we start, it's helpful to be able to identify the number of lone pairs for oxygen and nitrogen. In a lot of cases, you'll have to identify the formal charge for a given atom using the formal charge formula. But since oxygen and nitrogen are so often used in organic chemistry, you'll likely be able to identify the formal charge based on the number of lone pairs and bonds. So as a rule of thumb for oxygen, anytime it has two bonds and two lone pairs, like this example with H2O, oxygen will have a neutral charge. If an oxygen has three bonds and one lone pair, something like hydronium, it will have a positive charge. And finally, if it has one bond and three lone pairs, it will have a negative charge. For nitrogen, like our amine here, it has three bonds and one lone pair and neutral charge. And if it has four bonds, it will have a positive charge and no lone pair. So with that, let's draw in the lone pairs for this mechanism. So let's continue with the mechanism for imine formation. In this reaction, we're going to use 3-pentanone and reacting it with methylamine and a generic acid. In the first step, the amine attacks the carbonyl group. This will push the electrons from the carbonyl group onto the oxygen. So our amine attacked the carbonyl group, so we can label this step as nucleophilic attack, or Na. In the next step, the oxygen gets pronated, removing its negative charge, so we can label this PT. Now in the next step, we can see that it's another proton transfer. This time, a base will pronate hydrogen from the nitrogen. This gives us what looks like a hemiacetal, but it's actually known as a carbonylamine. In the next step, we see yet another proton transfer step. This time, the hydroxy group will get pronated, turn it into water, which we know is a good leaving group. Next, water does in fact leaves, and this is facilitated by the nitrogen's lone pair pushing here, forming a carbon-nitrogen double bond. So we can label this step loss of leaving. This leaves us to our last step. As we talked about earlier, anytime a nitrogen has four bonds, it will have a positive charge and no lone pairs. Our intermediate here will get depronated by a base and forming our imine product. So we can see that this mechanism involves quite a few steps. What I'd like to do to make it easier to memorize it is to break down the mechanism into two parts. We can break down the first three steps, which forms our carbonylamine, And for the final three steps, we know that the carbanoamine gets converted into our imine product. So in this example, we're asked to propose the mechanism for the following transformation. And for imines, we know we can break down the mechanism into two parts. So let's write them down so we can use it and work through this example. In the first part, the steps are Na, PT, and PT again. And we know this is going to give us a carbanoamine. In the second part, we have PT, lost the leading group, and PT again. This will give us our imine product. So the first step we know is nucleophilic attack by a primary amine. Next we have proton transfer. And then we have proton transfer again. We know the result from this is a carbanoamine intermediate. We'll continue with another proton transfer. And now we have water as good leaving group, so let's draw on that mechanism. And finally, we have another proton transfer giving us an imine product. Now let's take a look at the mechanism to form enamines. The mechanism of enamines is the same as imine, but slightly different in the last step. Let's start by drawing in lone pairs in the mechanism. So let's go over the mechanism. In the first step, our secondary amine will attack the electrophile, followed by proton transfer. So let's go over the mechanism. In the first step, our secondary amine will attack the electrophile, followed by proton transfer. And then another proton transfer giving us the carbanoamine intermediate. We know after this there are 3 additional steps to form our enamines. So we have proton transfer to give us a good leaving group. Next we have a loss of leaving group. So here's where the mechanism for enamines differ from imines. You'll notice we have a positive charge on nitrogen, but since it's a secondary amine, it no longer has hydrogen. Proton transfer enamines comes from alpha carbon, and since the carbons on either side are the same, we can choose to pronate either one of them. So we pronate the hydrogen here, pushing the electrons to go back to nitrogen. In this example, we can use what we previously learned about enamines to draw a mechanism for this transformation. The first step we know is nucleophilic attack by a primary amine. Next we have proton transfer. Followed by another proton transfer. We know after this, we form our carbanoamine. We'll continue with another proton transfer. And now we know we have a good leaving group. And finally, another proton transfer from the alpha carbon. You notice we only have one alpha carbon here, so let's draw in the last step of this mechanism. Let's take a look at why tertiary amines are unreactive towards aldehydes and ketones, whereas our previous examples of primary and secondary amines are reactive. We can show the reason why tertiary amines are unreactive by drawing in structures. If we take a look at the structure of primary and secondary amines, we can see these products contain product hydrogens. This is something tertiary amines does not have, so the equilibrium for this reaction will favor reagents. Now let's see if we can come up with a mechanism for this reaction. Now this reaction might look difficult to conceptualize at first, but the only difference here is that this is an intramolecular reaction. You can see from the starting material we have a primary amine, and we know that primary amines will produce imines. The mechanism for this is of course no different. The first step is nucleophilic attack. This step, of course, forms a ring. The next step we know is proton transfer. The next step is also proton transfer. The next step is another proton transfer. This is followed by a loss of leaving group. And finally, another proton transfer giving us the imine product. So similar to our last example, this is an intramolecular reaction. The difference here is that instead of using a generic acid, we have H2SO4. We know from the last example that an intramolecular reaction will form a ring. Let's identify our nucleophile and electrophile. Let's count the number of carbons. Including nitrogen, we know we have a 5-member ring. Let's check to make sure we have the correct number of carbons. Now we notice we have 2 alpha carbons. Now we could depronate a hydrogen from this carbon or this carbon over here. But you'll notice this one is more substituted. This would give us our major product. So let's see if we can come up with a product for this reaction. For this reaction, we have a primary amine, hydronium, and acetone. It would be helpful to predict our product if we draw out acetone. You notice that acetone is in fact a ketone. We know that a primary amine and a ketone under acidic condition produces an imine. So a shortcut I like to use is this. We know that reactions involving imines also produces water. What this means is we can take away water from the left-hand side. So if we look at our reagents, we can see that we can take water here. We simply replace the oxygen with a nitrogen for our product. So reactions involving imines and enamines are reversible. They can be hydrolyzed back to aldehydes or ketones. So let's try to reverse this reaction with an enamine. Let's write down the steps that we learned earlier, but this time in reverse. So the first step we have is proton transfer. And if you recall, the next step is loss of leaving group, but in this case we'll gain water. The next step, water gets deprotonated. The next step, nitrogen gets protonated. In this step, hydroxy group get deprotonated. Of course, in the last step, we lose the amine to produce the ketone. Let's take a look at how imines can be hydrolyzed back to another higher ketone, an amine. Again, let's start by writing the mechanism for imines in reverse. So in the first step, we have proton transfer. In the second step, we previously had loss of leaving group, but in the reverse reaction, we have water attacking. Next, we have deprotonation of water. And if you recall, this gives us our carbanoamine. Next, the nitrogen is protonated. Next, the hydroxy group get deprotonated. And finally, in the last step, the amine group departs, collapsing the tetrahedral intermediate and forming a ketone primary amine product. So let's take a look at what happened when you react a tertiary amine with H3O+. So this reaction is really hydrolyzing an enamine into an aldehyde and amine. Let's go through the mechanism. In the first step, we have proton transfer. And if you recall, the next step is loss of leaving group, but in this case, we'll gain water again. The next step, water gets deprotonated. Nitrogen gets protonated. The next step, hydroxy group gets protonated. And if you call the first step in enamine formation is nucleophilic attack. Of course, in this last step, we lose the amine to produce an ketone.